Now we will discuss a very important property of steam turbines, which is compounding of steam turbines. If only one stage comprising of single nozzle and single row of moving blades are used, then the flow energy or kinetic energy available at inlet of machine is not absorbed fully by one row of moving blades. It means to say that for high rotational speed, all the available energy at inlet of machine is not utilized, which is simply wasted at exit of machine. Also, we know that for maximum utilization, velocity of steam should be minimum or negligible. Hence, for better utilization, one should have a reasonable tangential speed of rotor. In order to achieve this, we have to use more rows of moving blades with a row of stationary blades between the every pair of moving blades. Now, the total energy of steam available at inlet of machine can be absorbed by the moving blades in succession until the kinetic energy of steam at the end of the last row becomes negligible. Okay, the overall concept of compounding is to utilize a maximum energy from the steam. So if you if you make a steam to undergo expansion in a single row of uh, rotor or single row of blades, then complete energy will not utilized properly. So that is why we will use a concept called compounding in order to utilize complete energy from the steam. Now let us discuss about different methods of compounding. Among that, the first one is velocity compounding of impulse turbine. This consists of set of nozzles and rows of moving blades. You can call it as rotor. Moving blades, the rows of moving blades can be called as rotor, and rows of stationary blades we can call it as stator. Stator means it is stationary, so rotor means which rotates. Figure shows corresponding velocity compounding of impulse turbine. This is the velocity compounding of impulse turbine. The function of stationary blades is to direct the steam coming from the first moving rows to the next moving row without appreciable change in the velocity. All the kinetic energy available at the nozzle exit here, all the kinetic energy is available at the nozzle exit is successfully absorbed by all moving rows. These are the moving rows or moving blades, and the steam is sent from the last moving row. This is the last moving row, and the steam is sent from the last moving row with low velocity to achieve high utilization. The turbine works under this type of compounding stage is called velocity compounded turbine. An example for velocity compounded turbine is Curtis turbine. Okay, in the diagram you can observe here we have set of nozzles and steam from boiler, okay, enters the nozzles. So in the nozzle what happens? The velocity increases and pressure reduces in the nozzle, and at the exit of the nozzle velocity is very high. This high velocity steam will enter into the moving blades. In moving blades its velocity drops, and again after that the steam at the exit of this first moving blade enters into the fixed blade. In the fixed blade you can observe there is no change in the velocity, and after the fixed blade again steam will enter into the moving blade. Again it undergoes drop in the velocity, and so this type of turbine we will call it as velocity compounded turbine. And I have already mentioned that the function of fixed blade is to just to direct the steam from one row of moving blade to another row of moving blades. In the fixed blade there is no change, and there is no change in the velocity and the pressure. Both pressure and velocity are constant in fixed blades. Now we will discuss about pressure compounding of impulse turbine. A number of simple impulse stages arranged in series can be called as pressure compounding. In this case, The turbine is provided with rows of fixed blades. In the diagram you can observe the rows of fixed blades, and which acts as a nozzle at the entry of each rows of moving blades. Okay, these are the fixed blades or nozzle which will be arranged at the exit of every set of moving blades. Here the total pressure drop of steam does not take place in a single nozzle, but divided among all the rows of fixed blades, which acts as a nozzle for the next moving rows. Figure shows the corresponding pressure compounding impulse turbine. Figure you can observe steam with high pressure and low velocity enters this first set of nozzle, or you can also call it as fixed blades. Here you can observe velocity increases in the nozzle, and again after the nozzle the steam enters the moving blade and hence velocity drops. Again once the steam passes over this another set of nozzle, velocity again increases. After the nozzle it enters moving blades, velocity again drops. And when you talk about the pressure, so before entering the nozzle pressure was high, while passing through the nozzle pressure reduces, and after the nozzle it undergoes steam passes over moving blade. In the moving blade there is no change in the pressure will be constant over the moving blade. And again once the steam passes over the nozzle pressure again reduces, and after passing over this moving blade, during the moving blade pressure again constant. So this type of arrangement we will call it as pressure compounding of impulse turbine. Okay, we will discuss about pressure velocity compounding. In this method high rotor speeds are reduced without sacrificing the efficiency or the output. Pressure drop from the chest pressure to the condenser pressure occurs at two stages. This type of arrangement is very popular due to simple construction as compared to pressure compounding of steam turbine. Pressure velocity compounding arrangement for two stages is as shown in the figure. First stage and second stage taken separately are identical to a velocity compounding consists of a set of nozzles and rows of moving blades fixed to the shaft and rows of fixed blades to casing. The entire expansion takes place in the nozzles. The high velocity steam parts with only portion of the kinetic energy in the first set of the moving blades and then passed on to fixed blades. Here only change in direction of jet takes place without appreciable loss in the velocity. This jet then passes on to another set of moving blades where further drop in kinetic energy occurs. Okay, in the diagram you can observe pressure velocity compounding steam turbine. Okay, steam with high pressure and low velocity enters the nozzle, set of nozzle. Here velocity increases and pressure drops. So now high velocity steam will pass over to the moving blades. Here in the moving blades you can observe there is no change in the pressure but the velocity reduces. Again after moving blade steam passes over set of fixed blades. In the fixed blades the velocity is constant here, just this fixed blade directs this steam to another set of moving blades, and this moving blade again we know that the pressure is constant but the velocity is decreased. So after this stage another same stage is there in the beside. So this type of arrangement we will call it as pressure velocity compounding turbines. Now we will discuss about effect of blades and nozzle losses. The losses in flow over blades due to friction, leakage and turbulence are not negligible in most of the cases. These losses reduce the velocity obtained at the outlet of blade and is less than the velocity which would be obtained in the loss-free flow. The ratio of the actual velocity at the exit of the flow passes to the ideal exit velocity is called blade velocity coefficient or nozzle velocity coefficient. Thus, that term can be represented by the symbol Cb, which is called blade velocity coefficient or nozzle velocity coefficient. So VE by VE dash, where VE and VE dash are the actual and ideal velocity of nozzle or stator or rotor blades.